Hello students, this week you'll be working on an expected value activity. It's going to consist of a mock casino and you playing different games. Your job is going to be to calculate the expected value for each game and then determine total wins and losses. So let me give you a couple examples just to give you an idea of how you might go about doing the activity. Remember, you're allowed to work with other classmates, and I've set up a Google Jamboard for our class in case you want to share work with other students. This being said, let's jump right in and look at a few examples. So, example 1. Suppose we have a game that costs $3 to play. You draw one card, and if the card is red, you win $5. If the card is black, you lose. The first question, what is the expected value of the game? And then the second question, if you played the game 100 times, how much would you expect to win or lose? The first thing we want to do is remind ourselves what exactly is an expected value. Let me put it up at the top here. Let's recall that an expected value is equal to the amount of money you might win in a game times the probability of that win, plus the amount of money you might lose times the probability that a loss occurs. So there are several key components that we're going to have to calculate and understand. We're going to have to look at how much money we're winning and losing, and then we're also going to have to look at the probability that a win occurs and a probability that a loss occurs. I want to start by focusing on the win portion of this expected value equation. That is, how much money are we going to win? And what is the probability that a win occurs? Let's start with the first part, which is how much money are we going to win? Well, notice that your game costs $3 to play. If you choose a red card, you win $5. So at first we might say, oh, we win $5, but remember, it costs $3 to play. So the actual winnings is going to be the $5 that you win, but take off that $3 it costs to play. So your net win or your net gain is $2. So we win $2. Now, what's the probability of that happening? Well, let's see. If the card is red, you win. Okay. Well, I have our whole sample space drawn out for us to kind of help us. And if I'm looking at these cards, I see that there's 52 total cards in my deck. And of those 52 cards, 26 of them are red, right? So I have 52 cards, 26 of which are red. Or in other words, we could say that half of the cards, 26 out of 52, or 1/2 of the cards are red. Therefore, the probability that we select a red card is simply 1/2. The probability of a win occurring is simply 1/2. And so for the win portion in our expected value, we're going to have 2 times 1/2. And how do we multiply? We take 2 over 1, that whole number divided by 1, times 1/2. And we can do a little quick cross cancel if you want. 2 divides into 2, 2 divides into 2. And that gives us 1 times 1, which is 1, over 1 times 1, which is 1, or simply 1. So that first portion, the win times the probability of a win, is just positive 1. Let's now take a look at our loss. We have to talk about the amount of money that we're going to lose times the probability that a loss occurs. So how much money are we losing? Well, really, we're only losing the amount that we have to pay to play the game. So our loss amount is actually just $3. Now, what's the probability that that loss occurs? Well, that loss occurs if I choose a black card. And the black cards are the top portion. And again, just like before, there are 26 black cards in the deck, or half of the deck is black, right? Half of the deck, 26 out of 52. So we would say that the probability of choosing a black card is just like the probability of choosing a red card, which is 1/2. Let's calculate out that expected value portion with the losses, and that's going to be 3/1 times 1/2. Nothing cancels, so we multiply straight across. 3 times 1 is 3, and 1 times 2 is 2. But remember, this is a loss. So I want to designate this as a loss with a negative number. We are losing $3 or a net gain of -3. And therefore, I'm going to keep that negative through, and this is important not to forget it, that this is going to be a loss portion. So there's a negative on that 3/2. Let's put these two together to get our total expected value. So what is the expected value of the game? Well, the expected value comes from the win portion, which is +1, added to the loss portion, which is -3/2. And you can either convert -3/2 to a decimal, or if you like me, you like working with fractions, so I'm going to convert 1 into 2/2 to get a common denominator. And I'm then going to take 2/2 plus -3/2 and add the numerators, keep the denominator the same. 2 plus -3 is the same as 2 minus 3, which is -1. Pulling out our calculator to convert this into a decimal, or if we like a dollar amount, so we are going to be losing -1/2 of a dollar, which is equivalent to saying that we're losing -50 cents. 1 divided by 2 is 0.5. We would say that the expected value for this game is -50 cents. What about that second question? If you played the game 100 times, how much would you expect to win or lose? Well, how do we calculate that? We simply take the 100 times that we're playing our game and we multiply it times our expected value, -0.50. That's going to tell us how much total we expect to win or lose. And if we take 100 times -0.50, that just tells us that we would expect to lose -$50. So we would expect to have a loss of $50 if we played the game 100 times. Okay, now that example wasn't too bad, I hope. Let's take a look at one more example, just slightly more complicated. Example 2. This game costs $10 to play. This time you draw 2 cards. If both cards are the same face card, that is, you have 2 jacks, or 2 queens, or 2 kings, then you win $450. Otherwise, you lose. Well, the way we begin this problem is just the same as we did the last one, and that is we want to remind ourselves what that formula is for expected value. Remember, expected value is the amount of money we win times the probability that a win occurs, plus the amount of money that we lose times the probability that a loss occurs. We'll start again with our wins. We're going to focus first of all on the amount of money we win, and then we're going to multiply that times the probability a win occurs. But this time, since we're selecting 2 cards, that probability is just slightly more complicated. Let's start with our win amount. If you draw 2 cards that are the same face card, namely 2 jacks, 2 queens, or 2 kings, then you win $450. But remember, our net win is going to be the win amount, take away the amount it costs to play. So our net win can be found by taking our $450 winnings, subtracting off the $10 we started with, and so that means our net win or our net gain is going to be $440. Now we're going to need to multiply that times the probability a win occurs. And for that, I need to do a little bit of thinking, a little bit of scratch work. In this game, we're actually selecting 2 cards. So let me draw 2 cards that I'm picking. Now, there's a couple things that are understood. When I pick these two cards, I'm not going to replace. So I draw one card and then I draw a second card without replacement. Let's take and consider what is the probability that both of our cards are jacks. Well, what's the probability that we have two jacks? Let's start there. Well, how many jacks do we have in our suit? Notice there are 4 jacks in the suit. A jack of spades, a jack of clubs, a jack of hearts, and a jack of diamonds. So we have 4 total jacks. We have 4 jacks out of 52 playing cards. So we would say that for that first card, the probability of just getting a jack on that first card is 4 out of 52. So let's say we pick a jack. Now we have to draw a second card. Well, the first thing we notice is that our denominator has changed. Because we drew one card and we're not replacing, that means we have to reach back into the deck, but this time there are 51 cards in the deck. So the denominator now becomes 51. And what's the probability now that we select a jack on that second chance? Well, that first one we already said we're picking a jack. So that only leaves 3 jacks left for us to choose. So the probability of getting a jack on the second card would be 3 out of 51. Now, I like to simplify fractions before I actually put things together, so I'm going to go ahead and simplify. I know that 4 divides both into the numerator and the denominator of this fraction. 4 divides into 4 one time, and 4 divides into 52 13 times. So the probability for that first card being a jack would be 1 times 1 over 13. Likewise, I'm going to cancel that second fraction. 3 divides into 3 once and into 51 17 times. And so that means the fraction 3 over 51 reduces down to 1 over 17. And so the probability that I select one jack followed by another jack, or if I like 2 jacks, is just 1 times 1, which is 1, over 13 times 17, which, pulling out a calculator, should give us 221. That's the probability of getting 2 jacks. So let me go back over here. That was my little thought process, but let's go back to what we were calculating, which is the probability of a win occurring. And let me start by writing the following. The probability that a win occurs first is going to be the probability that I get 2 jacks. Oh, I'm going to go back into my problem for a second here. I can select 2 jacks, or I can select 2 queens, or I can select 2 kings. And what was it when we did probability and we saw the word or? First of all, when we see the word or involved, what are we thinking with this probability? Do you remember our rule? We have that rule that the probability of A or B occurring, as long as the events were mutually exclusive, right? As long as they both couldn't happen at the same time. So as long as they were mutually exclusive events, finding the probability of A or B is equivalent to finding the probability of A plus the probability of B. Do you remember that? When we saw or, and our events were mutually exclusive, meaning they both couldn't occur at the same time, then we found that probability by adding them up. So that means to get the probability of a win, we take the probability of selecting 2 jacks plus the probability of selecting 2 queens plus the probability of selecting 2 kings. Our win consists of 2 jacks or 2 queens or 2 kings. And our probability statement told us we can find that by adding up those distinct probabilities. That gives me a focus and a direction to go. I know what the probability is for selecting 2 jacks. That probability was 1 out of 221. Now, do I know what the probability is for selecting 2 queens? Let's put your thinking caps on. When I went through this whole discussion about selecting 2 jacks, did it matter that I started with a jack? Could I have just as easily started with a queen? Is the probability not the same? Well, let's look at our queen column. Notice just like with the jacks, there are 4 queens, a spade, a club, a heart, and a diamond. And so the probability of selecting that first queen is going to be 4 out of 52. Once I select that first queen, I have 3 queens left out of 51 cards, so I'd have to multiply that by 3 out of 51. And it looks to me that I get the exact same probability occurring. The probability of selecting 2 queens is exactly the same as the probability of selecting 2 jacks. That is, the probability of getting 2 queens is 1 out of 221 again. And how about kings? Well, kings, they're going to be the same thing, right? Kings are just another face card. And the probability of getting 2 kings is exactly the same as the probability of getting 2 queens, and that's exactly the same as the probability of getting 2 jacks. To get 2 kings, I'm looking at the king column. There are 4, and the probability of selecting a king and another king is 1 out of 221. Oh, so putting this all together, what does that tell us? So this is a doozy. This one's a long one. That tells us we take 440 times, and now I have 3 fractions, all with a common denominator. So I add my numerators, 1 plus 1 plus 1, which is 3. And then I'm going to take 440 times 3. And when I take 440 times 3, that gives me the numerator of 1,320 out of 221. This was the win portion in my expected value problem. Just so I don't get things too confused, let me erase and put this up here. That means the expected value of my game comes from the winning portion, which is positive 1,320 over 221. Plus, and now I have to focus on my loss. So let's erase a little bit and let's focus now. How much would I lose times the probability of a loss? So I erased a little bit, but I'm going to keep one thing. The one thing that I want to keep just temporarily is this number right here, 3 out of 221. That was the probability of getting 2 jacks, plus 2 queens, plus 2 kings, or in other words, that probability was the probability that a win occurred. Okay, so I just want to hold on to that while I erase everything else. So everything else is gone, and I'm going to hold on to that probability. Why? Because I'm looking ahead and I'm going to right now talk about the loss portion, which is how much money do we lose multiplied by the probability of that loss occurring. So how much money do we lose? Well, that's the amount of money that it costs to play the game, which is $10. So we would say that we lose $10 by playing this game. Now, what's the probability that that's going to happen and I don't win anything? Well, I lose if I don't draw 2 of the same face card. So if I drew a jack and a queen, or if I drew an ace and a king, or if I drew a 7 and a 6, or 2 2s, or a 5 and a 4, or all different kinds of combinations and possibilities. In fact, there's just too many for me to even consider and count right now. So the way that I'm going to evaluate the probability of a loss is going to use the fact that the probability of a win and the probability of a loss add up to give us 100%. A win and a loss are what we say, or what we call complements of each other, right? Complements are one and the opposite. You either win, or if you don't win, then you lose. Conversely, you either lose, or if you don't lose, you win. So they're complements of each other, okay? So when we talk about complements, do you remember a rule we had from probability about complements? Well, there was a rule that said that if you have an event and you have a complement, that the probability that an event occurs is equal to 1 minus the probability that the complement of the event occurs, and vice versa, right? The probability of a complement is the same as 1 minus the probability of the event. This comes from the fact that the probability of winning plus the probability of losing together gives us 100%, gives us our 100% total. So when I look at calculating the probability of a loss, I'm going to take 1 minus the probability of the win occurring. Why? Because I'm smart. No, it's because I've already got the probability that a win occurs. So it would be smart of us to go ahead and use that number and not have to worry about counting all the other possibilities that occur when you lose. So let's put this into our equation here. What is the probability of a win? The probability of a win is 3 over 221. So the probability of a loss is simply going to come by taking 1 minus 3 over 221. We need a common denominator, so I'm going to go ahead and put negative 10 and now multiply, common denominator being 221 out of 221. Then we're going to subtract. And so that gives me 221 minus 3, or 218 out of 221. And when I multiply 218 over 221 by this negative 10 in the front, I put it in the numerator over 1 and multiply straight across. So that's going to give me negative 2,180 out of 221. This is our loss portion in the expected value equation. We expect to lose this loss portion, negative 2,180 divided by 221. Combining that with our positive part in that expected value equation gives us a common denominator of 221, but a numerator. So we want to take 1,320 plus a negative, or if we like, subtract 2,180. So that's going to give us negative 860 divided by 221. And we want to pull that into our decimal, or our money, and out of the fraction and into a decimal so we can look at it in terms of money. And that means our expected value, rounding to the nearest hundredth place, is going to be negative 3.89. Negative 3.89. Even with a win of $450, we still are going to have an expected value, if we play this game, of negative $3.89. We finish by doing part 2, which is, if we played this game 100 times, what would you expect to win or lose? Well, to calculate that amount, we simply take the 100 times we're playing the game, and we multiply it by our expected loss, which is negative 3.89. Doing so gives us an expected total loss of $389. Wow. That was a lot of thinking. Anyways, I hope this was helpful. I hope this made sense for you. Most importantly, with this expected value activity, I want you to really kind of have fun. It's a way to review, to test and see if we have our knowledge down, but also to have fun in the process. If you have any questions at all, don't hesitate to reach out to myself, our embedded tutor, or any of your classmates. Good luck.